Okay. To tell me a story here, I'm gonna tell you a story in motion. If you have your notebooks, I want you to graph the position time graph that goes with this. Okay. Okay, so we're gonna start off with this one. Okay, I'm moving at some. Okay, this means I'm starting the stopwatch, right?
Alright.
This. Okay? Yeah, that does. Okay, so here we go. I'm moving along at constant velocity, start the stopwatch, walk for a while, and then I slow down to rest. So once again, I'm walking at constant velocity for a little bit, and then I gradually decelerate to rest. Okay? I want that in a picture. I want that in a motion picture.
Like, do we go out and do it?
Well, no, you just do it on your paper. So here's position as a function of time. Okay? Okay, who thinks they've got it?
Johnny thinks
No, I don't.
You don't?
I thought it did. No.
But Ian does. Come on up, Ian.
I think I
Yeah.
What do you got?
I think I go ahead and say it's like they told me they told me to do
Okay, anybody wanna say something different about it?
The color, I don't like to.
Okay?
that.
Should I get up or just?
Go ahead.
Take your time, bro.
Okay, can I change the color too?
Sure.
Awesome.
Oh,
You get so. Yeah. You're saying that he keeps
Doing what?
Yeah.
Wait, you slowing down.
Thank you, okay.
Okay,
Yeah.
I'm still gonna say no.
No, wait.
Wait, he's, no, wait. Okay, come on up. Come on up.
How about now? I'll let
Okay,
Jamie go.
no, no.
There we go.
No. Here we go. I'm gonna go back for you here. We gotta clear this nonsense off.
Make it not pink.
There you go, now go.
Make it pink.
Gross.
Hermiston colors.
Okay,
Well, no, but you started the stopwatch.
it's
after
closer, it's
you-
closer.
Didn't you start the stopwatch?
Okay, maybe I need to go through my little video again here though, right? So there's kind of almost like two parts to this. So part one, I start it and I'm just walking at constant velocity. Now part two, I slow down to rest.
So did you speed
So I
up?
take a few steps at constant velocity and then I decelerate. Okay?
Yeah, so we'll.
You wanna take a crack at that?
What did it do, what, river drew, just?
Yeah. No.
Just that, but flipped around?
No, because you can't start at a distance, you're starting at zero.
Ah, exactly.
Oh, tools. So
Yeah.
this is-
You guys, hey, you want to try that? You got an idea? Who's got that? Who's been from that half? Somebody over here. Come on, what do we got?
You haven't even been to yet.
There's so many
Brandon
different X's
does
and
it.
Y's I'm gonna work with, you know? It's-
Or Sam.
If you're shy, just tell me what to do and I'll drop for you.
Yeah.
Dave's got it. Oh, here we go.
Get it, Brandon.
Well, you still have to go down.
Wait, those ones
No,
up.
you don't have to go down.
But you had to slow down.
But you didn't go, okay, but it's
Oh,
very,
yeah,
very
yeah,
close.
yeah.
No, but you didn't go. He didn't go back to his original.
Okay,
Yeah.
so if you want to erase any part of that, what could you do?
Erase the bottom.
Erase like where it crosses that line.
Right, so that's pretty good. So
Good job.
without this part right here, he had it. Everybody agree?
You were
I was right.
What's the
No,
difference?
no,
It's
his
empty.
part
It
was-
was
he
like-
was pretty great.
But
I
I didn't
did.
get a constant, that's why.
So, right, and maybe if we wanted to draw it, maybe with a little, maybe a little bit better way of drawing it might be like this. How about, our first part, everybody agree with me, is gonna be part one, when I'm traveling at constant velocity, what's that gonna look like? Yeah, it's gonna look like a straight line with constant slope, right? Okay, because remember, the slope of a position time graph is equal to velocity, right? Okay, then that's part one. Now part two, we're gonna go from that velocity to zero at a uniform, right? So we're gonna gradually, starting right there, our slope is gonna gradually change to 0. Right? And then if part 3 was, I just stand here, then part 3 would have just looked like that. Right? Make sense?
Oh, yeah.
If I draw it, maybe it'd be better if I drew it like this, it might be more, it might illustrate that part better. So there's part 1, there's part 2, and that would be part 3 if I just stood there. Okay? Okay, let's draw this in a different way. That tells the story, doesn't it? Okay? But let's tell the story in a slightly different way now. Let's make a different kind of motion. Let's make a velocity time graph. So now we've got velocity as a function of time. What's it going to look like now? What is part A or part 1 going to look like now? It's going to be just straight, isn't it? Right? Because my velocity is constant at the beginning and positive, right? So this part right here, it just look like that, wouldn't it?
Yeah, this would be what everybody was trying to do the first time around.
Right. Now, part 2, my velocity is going to uniformly transition from this value to 0, right? So part 2 is just going to look like that.
Why would your velocity?
Because
you
started
because I started the stopwatch.
Walk down.
Remember, I started it when I was already moving?
Oh, okay.
Right? And then part 3 looks like what? Part 3, I just stood there.
So it's
Timer.
flat and 0.
Yeah. Right? Everybody agree?
Yeah.
Okay, good. Let's add some numbers to this. Let's make this quantitative. So this time I'm gonna say, okay, I was walking at a speed of, let's just say I was walking at a speed of 2 meters per second for 2 seconds during part A. Okay, so part A. Part B, it took me 4 seconds to decelerate to rest. And part C, I just stood. Okay, let's do a little physics. Let's do some kinematics. We haven't done that, right? We're gonna be getting back into that soon. Part A, what was my displacement during part A? What was it? 4 meters, right? Good. So and we can get that from just the equation displacement equals average velocity times time, right? Everybody agree? So that's going to give me a total of, this part right here is going to give me 4 meters of displacement. What about part 2 or part B? How am I going to figure that out? I can still use the same equation. No? And we know it can't be negative because you watched me do it, right? I'm going in the positive direction. Here's part A, now part B. I'm still going that way. I'm still displacing myself a little bit, right? But how am I going to figure that out? I just got to be able to plug in this stuff. What's T? So 4 seconds for part B, right? What's V bar though? My average velocity.
If you're sitting there.
Would be
So
4
Yeah.
seconds
Yeah.
and 0 meters per second.
Okay, but it's not 0, right?
You're slowing down.
What's my average velocity, dog? I start at 2 meters per second, right? I start because that's how fast I was going when I started to slow down, and then I ended at 0. So what's the average?
Oh.
1, right? Yeah, average of 0 and 2 is 1. So 1 meter per second times 4 seconds. This one also displaces me by 4 meters, doesn't it? Okay, now, I'm gonna maybe add some stuff up here. So I needed a spot there. total was 8, wasn't it? Was my total displacement? Any place where you can get that, you think? From our graph?
That's that right track.
That displacement is 8. Is there a way we could have found that from the graph?
6.2 support, 36
What was it?
What are you trying to find?
Well, I'm trying to find, so the total displacement, I had 4 meters during part A and 4 meters during part B for a total of 8 meters of displacement.
All on the cosine, right?
That's way too complicated.
You add them.
Add what?
Spin.
Yeah, okay, but now, ignore the fancy kinematic stuff and just tell me from the graph, could I have gotten those same numbers? Could I have gotten, how?
Rise over.
Well, if it was labeled, you could see that you can have 4 in part A and 4 in part B. With that.
Okay, how can I see that, because part A ended right here, didn't it?
That ends at 2.
It ends at 2, right? So this is part A and that's.
But you'd be able to see the velocity.
You were going at 2 meters.
Yeah, you-
Okay.
you'd be able
Now,
to
I
find
did
the
put units
velocity.
on here, so that's +1 and that's +2 and that's 1 and that's 2.
You multiply the velocity by the time. Yeah, velocity by the time.
Okay, what does that look like on my graph?
2 times 2.
Okay, but what is that describing? You're right.
Area.
It's an area, isn't it?
Oh, it's a square.
Yeah, it's an area under
I
the
said it
curve.
was a square. Right when you wrote. Did you hear me?
Stop being a Donald Trump.
I swear I said it was a square. I was like,
So that area is 4, isn't it?
You're
Right.
just calling it shapes ice.
Yeah.
Right, but I think that's 4. Well, what's this one? It's a triangle with a base of 4 and a height of 2,
Half of it.
so it's 4 also, okay?
I said it was wrong.
Does that make sense? If you think about this, right?
Yeah.
Think about now, you gotta focus for a second, so this doesn't escape you. You gotta think about what area would represent on a graph like this, right? Area is 2-dimensional. Agreed? Okay, so what are our 2 dimensions here? Well, the vertical dimension represents velocity, right? Velocity, let's just focus on the units for a second. Velocity, units of velocity are meters per second, all right? The horizontal dimension represents time, okay? So if I multiply those 2 dimensions together, think what we're doing. We're taking a velocity dimension and we're sweeping it out in time to generate area. Think about the product of the dimensions. Meters per second times seconds gives us meters, right? Meters per second times seconds gives us meters, right? So the units work out, but just because the units work out doesn't mean it's true, but it is true. But it is true, because that's the way those dimensions couple together, okay? So these are simple examples because we had either a constant velocity or a uniformly changing velocity, which is the same thing as constant acceleration, which we'll explore even a little bit more in a second. But here's the cool thing about this. If you're in, have been, or will take calculus, this sets us up to do some interesting stuff. Because we could take the same concept where we've got a velocity function and time, and we could do something complicated. Like we could look at, for example, the velocity of let's say we're gonna hit a baseball off of a tee. Okay, so it's at rest initially, and what does that look like if we say it does something like this? And then that's where it starts to leave the tee and goes at constant velocity. If we want to look at how far the baseball moves while it's being deformed by the bat, right, while it's in contact with the bat, that would just be the part of the graph right there, wouldn't it? Okay, so all we'd have to do is the same process. If we could add up the area described by that function, meaning the area under the curve, then that would tell us how far it moves. Well, that's what calculus does. For non-geometric shapes, for curvy shapes. That's one of the 2 big jobs of calculus, is to be able to add up areas under curves.
How would you do that?
Well, it would look, in calculus, it would look like this. It'd look like the integral of v of t dt from 0 to, call it t1. which is when when the ball springs off the bat. And you guys don't have to do that now, but you will. When you take calculus, that's no big deal. That's what you do in calculus. And so you can see that physics takes on a whole different dimension in a way. I mean, you're able to do problems that aren't so contrived, where it's just always constant velocities, constant accelerations. You can deal with situations that are more real world if you can just add the ability to do what we're doing with a little higher level math. But what we're doing is just a model for what you could do later that's even cooler, right? Okay, so then let's look at some of the characteristics of this velocity time graph, because you already told me yesterday, for a position time graph, you told me, and this was interesting, and let's just quickly reinforce this point. If we've got something, let's say that this is, once again, let's take an interesting, like calculus type problem, where we've got, say, position that's changing in a weird way, that's changing in a curvy way, not just by straight lines. Say we've got, this is our function for position. Say it's doing something like that. Okay, so it's starting off, the velocity, which is the slope, is 0, right? And then what's happening as time progresses? What's happening to the velocity? Okay, it's starting to increase. And there's that concept we talked about yesterday of tangent line, remember? Where we said, if we look at the slope of the tangent line to the curve right there, draw that a little long, but you get the idea, right? The slope of the tangent line to the curve at that point is really the same thing in calculus as the slope of the curve at that point, right? And our sort of our justification for that yesterday, our non-calculus justification, was just that if we were to zoom in on that point, say we were going to center the frame on that point and just zoom in and zoom in and zoom in without limit, as we zoom in, the curvature goes away, just like the curvature of the Earth is not at all apparent when you're on the surface of the Earth, right? It looks flat because you're so zoomed in a way, right? But zoom out to the moon and it's real curved, right? And so as we move up this curve, because the tangent lines change slopes, we can see that our instantaneous velocity is changing, right? Our speedometer would read really low down there, a little bit faster there. Speedometer would have the highest reading there, get a little bit lower, and up here at the top, the tangents doesn't have much slope at all, and so its speedometer reads a low number again. Make sense? Okay, questions on that? Right, we still could also, if we wanted to calculate an average velocity, that's easy to do. What if we wanted to calculate our average velocity from, let's just say this is 2 seconds up to 8 seconds? Well, that's fine. All we'd have to do is take those 2 points and connect them with a secant line. Secant line just connects 2 points on a curve instead of just grazing it at 1 point. And then if I took this secant line and calculated the slope of that secant line, that's my average velocity, right, over the interval. Does that make sense? Okay? Once again, we're not going to, go into huge detail with this stuff this year, but in the future, you will, right? So now, what about a velocity time graph? Let's explore the properties of that. So, we said that in this case, the area under the curve meant something. It meant displacement. What else can we get from the graph? What if we do something like this? Let's say that's my graph. What's going on there? I have moving in the positive direction. My velocity is increasing. What's it going to be? Constant what? Ah, okay. Constant acceleration, and the value of the acceleration is related to that line in what way? It's the slope. It's the slope, isn't it? Because think about the definition of acceleration, right? We said that acceleration, at least average acceleration, for us it'll be constant, is just equal to the rate of change of velocity, right? Wasn't it just change in v over change in t? Right? That's the definition of acceleration. Isn't that just the slope of this graph though, right? Because think what we've got here. Instead of y, we've got v, instead of X, we've got T. And so this is just like saying delta Y over delta X, which is slope of a line. Only for us, the Y is a V and the X is a T, right? So the slope of a velocity time graph gives us acceleration, right? If we go back to that real world example of the softball being hit by the bat, this is velocity versus time. Well, what does this tangent line right here represent for that specific time? What do you think? It's a slope, isn't it? Right, it's the slope of the curve, and so it must be the instantaneous. No. It's a velocity time graph, so the slope of the curve, meaning the slope of the tangent line, is instantaneous acceleration, isn't it? Right? So we could see on this profile right here where the softball is accelerating the most. It looks like it'd be right about there where the line's steepest. Okay? Make sense? Okay, so we get this kind of parallel relationship. On a position time graph, slope is velocity. On a velocity time graph, slope is acceleration. Right? Okay? Does that make sense? Okay? Let's tell a different story here. Let's say I'm going to draw the picture, and you tell me what it would look like on the front of the room. So,
Is velocity or?
yeah, good question. Velocity time graph. Lots of parts. 1, 2, 3, 4, 5 parts. So say start right here. What's part A going to be?
Speeding up.
Speeding up. Okay, click it on. Now what?
Then you're gonna slow down.
Yeah.
This
Okay.
Constant.
Okay, so here's part A. Part A was just this. Part A was I speed up. Part B is I'm going to move at constant speed. Part C,
Slow down.
slow down.
And then you go backwards.
Ah, okay, so we could break it up into even more parts if we want to. Maybe we can combine a couple of these. So there's A, B, and C. A, B, and C looks like this. Start from rest, speed up. Part B, I'm walking constant. Part C, I'm slowing down. Okay. Part D,
You walk backwards.
I'm increasing my negative velocity, aren't I? Right? So that means I left off right here. Now I'm going to start to pick up speed. There's the end of part D. What's part E? Constant negative velocity. Part F. Slow down, come to rest. Right? Make sense? Okay, so what does this positive red area right here represent?
Your distance.
Not distance.
Displacement.
Displacement during the first part, right? Okay, what does this, you like color coding here today. What does my green area for the second part represent? The negative displacement. Okay, interesting. Okay, so then what should, based on the picture, what should the total displacement be?
Zero.
It should be zero, because I ended up right where I started, right? Okay, so then, what do you think must be true about the sign of that area?
It's equal. It's equal to ABC.
It's equal in magnitude, but what about the sign?
It's opposite.
Yeah, it's actually negative, isn't it? Okay, that's another, and we could maybe justify that in a way because the velocity is negative there, isn't it? Right? Does that make sense?
Yeah.
So I'm multiplying negative velocity times positive time, but that is, once again, this in calculus. Some of you guys, sooner than later in calculus, when we get into this stuff, we're going to define areas under curves as being negative areas because that's what works, right? That's what got us the answer that we needed. Does that make sense? Okay. I don't know if, okay, what about this? One other thing. What if I wanted to know the total distance that I walked because my Fitbit broke and I want to get some idea how much exercise I got?
How much do you like?
Okay, but how can I get it from the graph?
You add the two parts.
Okay, I'm going to add the absolute value of the two parts, right? because the absolute value of the red part tells me the distance that I traveled. In this case, it's equal to the displacement, because you're both positive, right? But the green part, if I take the absolute value, even though the displacement was negative, distance is always positive, right? And so, although my total displacement was 0, hypothetically, let's say that the red area was 10 and the green area was negative 10. How much distance did I walk? 20. That make sense? Okay, right? So what if, well, nah, I don't know. I'll throw that one at you later. Okay, I think I'd be willing to let you get work a little bit there. Questions?
So we do need those from expected.
So we might. How much time we got? We got time, don't we?
Right.
Oh, we got a little time. Let me see if they're available. August. Talk amongst yourselves. I'll throw out a topic.
Jeez.
Oh, nice. Thanks,
Oh,
man.
you got three.
You're so sweet.
He's gonna come back.
Just very good. So
I tried to get like loads of Wi-Fi for
I tried to do something dumb.
I get
It's
some
gonna be
parts
two
of it.
at once.
I understand this, you can't change it.
Now you're skilled.
I can explain it to you.
Well, I don't know. By the way, if anyone needs to use a microwave, there's one right there.
Well, if you have help.
Did you know, yeah, you put the iPhone 7 in there, melt away the plastic outside of the headphone jack.
It'll charge you instantly. It has to be 2% and it'll charge you.
Yeah, it just has Trevor.
True.
Wait, did they let you try that?
Yeah, Trevor did it.
It's kinda like,
Wasn't it?
it's kinda
Well, it was his phone.
Let's try it.
Oh, is that the sound? Is the camera good? Pretty good looking.
I'm thinking the camera's way better.
Earlier this week. I could come over and sort of help.
I don't really, like, all my stuff is
But yeah, as soon as you get
And it comes with
like,
So one of the things I want you to do is maybe that's what you can do today, just play a little bit, play with those activities. If you wanna work, that's fine, Sid. Play with those activities on unit 2, they're good.
Are we gonna have a work day tomorrow on the fourth?
Yeah, we should have some work
Two
days.
part two.
Okay, so I can extend that deadline, I have a work day, I have a lab day planned for Thursday for sure. And so I'll kinda see about what happens tomorrow.
that work day or not?
Oh,
Lab day on Thursday for sure.
What's the last did you?
Lab day meaning you guys get to work on stuff.
Oh.
Let me think about that one just a little bit.
that was a top tier joke right there.